Finishing up lesson 12.1, we're now going to look at sequences that are defined recursively. Look at the top of the screen. A sequence that's defined by assigning an initial value, a beginning value, and then specifying the nth term by a formula involving one or more preceding terms is defined recursively. So take a look at example 5. Our first term is 2. You can see a sub 1, this notation indicates that that's the very first term. But then as we move on, you might say, well, what's the second term? Well, we're going to use this formula right here. If we let n equal 2, we can see a sub 2 would be n, which would be a 2, plus 3 times, well, a sub n minus 1, 2 minus 1 would be just a 1. So in other words, when n is 2, n minus 1 is the term right before it. It's a 1. We already know what a sub 1 is. In fact, they told us that it's a 2. So this is 3 times 2. 3 times 2 is 6. 6 plus 2 is 8. So our second term is actually an 8. To get to our third term, we'd let n equal 3 in this formula right here. A sub 3 would be 3 plus 3 times. Well, if n is 3, n minus 1 becomes 2, so that's a sub 2. We just found a sub 2 was 8, so that's 3 plus 3 times 8. 3 times 8 is 24. 24 plus 3 is 27. So here is our a sub 3. This is our third term here. We could take a look at our fourth term, a sub 4. A sub 4 n's equal to 4. We'd have 4 plus 3 times, well, we'd have a sub n minus 1. That's now the previous term, a sub 3. 4 times 3 times 27. 3 times 27 is 81. 81 plus 4 is 85. And we can proceed in this way. I guess we have to get to our fifth term. A sub 5 would be 4 plus 3 times, well, you guessed it, a sub 4. A sub 4 we just found was 85. 3 times 85 is 255, I believe. And we can add a 4 to that and get 259. Well, you can see the difficulty if we'd ask to find, say, the 100th term. To get the 100th term, we'd need to know the 99th term. Now, I'd like to show you how the calculator can come to our aid. Please press Mode. That's a button that perhaps you might have used a lot going from radians to degrees. But now we're going to go to our function bar, but change it to sequence. And we can hit Y equals. And you get a brand new window. Now, instead of having a sub n, we have u sub n. And you can see in our formula it's going to be n. You might wonder where n is. It's the x, t, theta, n button. Now when we press this x button, an n shows up instead of an x. I'm going to say plus 3 times. Now I'd like to have u of n minus 1. Please look at the 7 button. Just above it, you can see a lowercase u here. When you hit second 7, you get your u to show up. And then I'll say parentheses n minus 1. And this is how we indicate an n minus 1 term. There is no subscript. It's not written below the variable, but it's written right next to it in parentheses. The un min is actually your beginning term. If you look at the top of the screen here, n min is 1. So our first term was a 2, and we can hit enter. And at this point, I just want to be clear that you can hit second table, and then you can very quickly see what's happening. So you can see more or less what's going on. By the way, you can also catch a mistake I just made. My apologies. Some of you probably already caught it. A sub 5 with the n, pardon me, 5 plus 255 would be 260. Made a silly arithmetic mistake. Didn't have our n term being 5 there. But you can see how the calculator just caught that for us. Everything else is checking out. Okay, so this is a nice way that you can get some help. All right, let's look at one of the most famous situations you're ever going to see, the Fibonacci sequence. The Fibonacci sequence is going to start with 1. That's your a sub 1 or your u sub 1. That's your first term. Then you'd have a 1. But now look at this. Your next term, like if we'd want to find u sub 3 here, if n is equal to 3, that would be u sub 2 plus, and then 3 minus 2 would be 1. In other words, what you're really saying is to find the nth term, go and add up the previous 2 terms. And so we'd get 1 plus 1, of course, and that would be a 2. So that's your third term. You might guess that to find your fourth term, you'd add these other 2 terms, the 2 and the 1, you'd get a 3. To get your next term, you have to add your 2 previous terms. 2 plus 3 is a 5. If you wanted to keep going, 3 plus 5 would be an 8, and so forth. All right, well, let's go ahead and see if we could type in the Fibonacci sequence. I'm going to clear this out, and I'm going to make my u show up. Here's my second 7, parentheses n minus 1, plus, I've got to make my u show up again, second 7, and then I'll go n minus 2. And you can see where we're going. It's looking pretty normal, with one huge exception. You're going to say, now wait a minute, I have 2 initial conditions. How do I deal with that? Well, you're going to use brackets. Hit second, and then the left parenthesis, it's the button above the 8. You're going to have one bracket show up. And really, my first term is a 1, second term is a 1. This is going to sound kind of strange, but really you should be writing it backwards. You should put your first term to the right, second term to the left. We'll talk more about that, but that's the way the programmers have designed multiple beginning terms. You have to go from right to left. So when you've got a whole bunch of things, the very first thing on the right would be your first term, and then you'd go to your second, and if you even had more, you'd continue. Notice the comma was right above the 7, if you were wondering where that was. Then we'll go second, right parenthesis, right above the 9. And then what you can do very quickly is hit second table, and you can see that nice Fibonacci sequence taking place. 1, 1, 2, 3, 5, 8, and so forth. So that's the real nice setup. Tell you what, let's take a look trying to finish up this video with ample time. Writing out this sum. This is the Greek letter sigma. And for the Greek letter sigma, I'm going to have to restart OneNote here. But for the Greek letter sigma, that's like our letter S. And it's very much meaning sum. So sigma is going to mean sum everything up. So look, the beginning is always at the bottom. Start with k equals 0, end with the n minus 1 term. So I'm going to plug in 0. We'd get 2 times 0 plus 1. You could begin with the 0th term. In general, we'll begin with k equals 1 most of the time. Then go ahead, let k equal 1. You'd have 2 times 1 plus 1. Then you'd have letting k equal 2. We're just adding all these terms up. 2 times 2 plus 1. And you get the pattern. We're going to keep going until we end with an n minus 1. And that can look especially strange, saying, wow, this is just very abstract, an n minus 1 ending point. Well, look, 2 times 0 is just 0. Plus 1, you get a 1. 2 times 1 is 2. 2 plus 1 is 3. And here's 2 times 2 is 4. 4 plus 1 is 5. And we're going to keep going. If you really notice, it looks like we're adding up some odd numbers. Here we have 2n minus 2 plus 1. Negative 2 plus 1 would actually be an n minus 1. So you'll get a few homework problems that look something like this. Moving on to example 6. For example 6, thank goodness this is a problem where you can use your calculator. And your calculator is going to become such a huge help. Sometimes they'll just say, hey, add these up. Add up that formula from k equals 1 to k equals 12. Add up the first 12 terms. Well, look, press the math button. Go down to the summation at 0. Then hit enter. I'm going to type in n. By the way, whatever variable you'd like is good. Sometimes kids panic. They're like, well, it should be k. You could use any variable you'd like. But we're going to go from 1. I'm going to hit the up arrow and go to 12. Come in here and we're going to have, and by the way, there should be parentheses around this. They're understood parentheses at least. We'll have n to the third. And then we'll say minus 7n. And wonderfully, in a snap of the fingers, you've got a sum, 5,538. The calculator did all that work for you. Again, we've got some understood parentheses. You'll be able to definitely add up terms quickly. The book talks about using formulas. We're just going to use our calculator to make life easy. Last one. Express the sum using summation notation. That's sigma notation. And tell you what, we'll let n equal 1 or k equal 1. But look at these numbers. 1, 3, 5, 7. You might guess the next one's 9. And then we go up to 23. The real difficult part right here is knowing, first of all, what our formula is. And then also what our ending point is. What term we're going to finish with. And you might wonder how on earth you can represent odds. By the way, if you're really on your toes, you're going to say you just did that a moment ago in example 5. And you could say, well, that was 2k plus 1. Please remember, though, that was starting with k equals 0. I want to talk about 2k plus 1 real quickly. An even number could always be written as 2k or 2n, whatever you'd like. Perhaps I'll write just 2n. Obviously, multiply any value by 2, you've got something even. If you were to add 1 to that even number, of course you would get an odd, and that would be 2n plus 1. Similarly, if you were to subtract 1, you'd also arrive at an odd, 2n minus 1. So I guess what I'm getting at is, which one of these formulas really would represent this pattern if I'm starting with n equals 1? If you looked right here, and if you let n equals 1 for the 2n plus 1, sadly, that's too big. That would start off with a 3. But 2n minus 1 just might work. If you let n equal 1, 2 times 1 is just a 2. Subtract a 1. Hey, it looks like we're in business. We still have one remaining question. Where's our stopping point? Well, you know that for some n value, you will arrive at 23. So you could do a little side work and say, well, if 2n minus 1 is an odd number, and if it's equal to 23, how about we quickly add a 1, divide by 2, and quickly we see n is 12. Guys, that's your upper bound, and that's the end of the problem. So hopefully this is making sense. This is actually a 2-day assignment. Hope it goes well for you.